Hello friends, let's start this video by doing a quick recap of our last video. So in our last video we understood how to calculate the distance between two objects. However, the main takeaway was the distance between a point and a line. The distance between a point and a line is the perpendicular distance from the point onto the line. The same definition even applies for a point and a line segment, provided the perpendicular drawn from point intersects the line segment. So, if we wish to find the distance between the point A and the line segment MN, first we drop a perpendicular from the point onto the line segment MN. Now, we simply calculate the length of this perpendicular. Now you may be wondering, why are we discussing all these in the circles chapter? You will know it in some time. Now here is a circle with a chord in it. Now I want you to represent the distance between the center and this chord. Now this is nothing but the distance between a point and a line segment, right? And we know that the distance between a point and a line segment is the perpendicular distance from the point onto the line segment, provided the perpendicular from the point lies on the line segment. If you remember, in one of the theorems that we discussed earlier, we concluded that the perpendicular from the center of a circle onto a chord bisects the chord. Now, what does this statement indicate? It indicates that we can actually draw a perpendicular from the center of the circle to a chord in it. So therefore, the distance between the center of a circle and the chord is the perpendicular distance between those two. Now let's do a simple experiment. Let's move this chord between the center and the circumference of the circle. While we do this, I want you to observe how the length of the chord varies with the distance from the center of the circle. If we move the chord away from the center of the circle, the length of the chord decreases. If we move the chord towards the center of the circle, we can clearly observe that the length of the chord increases. So, from this we can conclude that if there are two chords in a circle, the length of the chord which is nearer to the center will be more than the length of the chord which is farther away from the center. So, the closer a chord to the center of the circle, the larger its length will be. That's the reason when we draw a chord passing through the center of the circle, it will be the largest chord in the circle, and it is also known as, yes, the diameter. Now, this observation leads to an intuitive question, which is, what if the chords are at an equal distance from the center of the circle? Then what relation will the chords have between them? Well, looking here, it seems like both of these chords are of an equal length. But in mathematics, we don't go by mere intuition. We go by proofs. So let's check if these chords are of equal length or not. So the statement that we are trying to prove is the chords at an equal distance from the center of the circle are equal in length. So to prove this, consider a circle with center O and radius R units. Let AB and CD be two chords in it which are at an equal distance from the center of the circle, that is from the point O. Now our aim is to prove that the chords are of equal length. That is, we have to prove that AB is equal to CD. So how will we proceed? As soon as you see this, the immediate idea that should strike your mind is forming triangles. Because without forming triangles or any known shape for that matter, we cannot proceed with any approach. So let's form triangles by joining OA, OB, OC and OD. And also observe that all these are the radii, which implies that their measure will be R units each. Now let's gather the information that we already know. We know that the distance between the center and the respective chords is equal. So let's consider the distance between the center and the respective chords to be D units. Also, let's consider the foot of the perpendicular from the center of the circle onto the chords AB and CD to be M and N respectively. We also know that from our previous theorems, the perpendicular from the center of the circle bisects the chord, which implies that AM is equal to MB and CN is equal to ND. Now we have to prove that the length of AB is equal to the length of CD. There are many ways of proving this. One way is, as soon as we see the figure, we can clearly observe that there are 4 right angle triangles. So, without wasting any second, we can apply the Pythagoras theorem for all of these triangles. If we do so, in the triangle OAM, we get OA squared equal to OM squared plus AM squared, from which AM squared will be equal to OA squared minus OM squared. Now we know that OA is equal to R units and OM is equal to D units. So therefore AM squared will be equal to R squared minus D squared units. In the same way, if we apply the Pythagoras theorem to the remaining triangles, we get the same results. That is, we get BM squared equal to CN squared equal to DN squared, which is nothing but R squared minus D squared. Now from this, we can conclude that AM will be equal to BM, which will be equal to CN and which will also be equal to DN. From this, we can conclude that AM plus BM will be equal to Cn plus Dn. Now we know that AM plus BM is equal to AB and Cn plus Dn is equal to CD. So therefore, we proved that AB is equal to CD, which implies that the lengths of these two chords are equal. So we proved that in a circle, if the chords are at an equal distance from the center of the circle, then those chords will be of equal length. Since we proved this statement, this will be a theorem now. Now it's time to prove the converse of this theorem. That is, if the chords are of equal length, then they must be at an equal distance from the center of the circle. Again, let's consider a circle with the center O and with two equal chords AB and CD in it. Now we have to prove that these two chords are at an equal distance from the center of the circle. That is, if we consider the distances from the center of the circle onto these chords to be D1 and D2, we have to prove that D1 is equal to D2. So how will we proceed now? Again, the most important step is forming the triangles. So first let's form them. Now proving that the distances to be equal means that we have to prove the heights of these two triangles equal. Since the distance between a point and a line segment is measured along the perpendicular. So our aim is to prove that the heights of these two triangles are equal. Now in both these triangles we can clearly see that all the corresponding sides are equal. That is, OA is equal to OC and OB is equal to OD. since they are the radii of this circle. And also it is mentioned that the chords AB and CD are of equal length, which implies that AB is equal to CD. So we can clearly see that all the three corresponding sides are equal, which implies that by SSS criterion, these two triangles are congruent. Now, how does this observation help us in proving that the chords are at an equal distance from the center of the circle? If you remember, we know that if triangles are congruent, then their areas are equal. So, from this observation, we can conclude that the area of the triangle OAB is equal to the area of the triangle OCD. We also know that the area of the triangle is equal to half multiplied by the base of the triangle multiplied by the height of the triangle. So let's find the areas of these two triangles and equate them. The area of the triangle OAB is half multiplied by AB multiplied by D, and the area of the triangle OCD is half multiplied by CD multiplied by D2. Now if we equate them, AB and CD will get cancelled since they are equal, and finally we get the result D1 equal to D2, which we are looking for. So we successfully proved that the chords AB and CD are at an equal distance from the center of the circle. So friends, we successfully proved the converse of this theorem. That is, in a circle, if the chords are of equal length, then they are at an equal distance from the center of the circle. We could have used the approach that we used in this theorem for this theorem as well. But I wanted to show you a different approach. The two theorems that we proved in this video are: in a circle, if the chords are at an equal distance from the center of the circle, then the chords are of equal length. And in a circle, if the chords are of equal length, then they are at an equal distance from the center of the circle. So friends, that's all for today, and we have added two new theorems to our list of theorems. Before we end this video, let's quickly summarize what we have learned so far. The distance between a point and a line is the perpendicular distance from the point onto the line. The distance between a point and a line segment is the perpendicular distance from the point onto the line segment, provided the perpendicular from the point lies on the line segment. The perpendicular from the center of a circle onto a chord bisects the chord. In a circle, if the chords are at an equal distance from the center of the circle, then the chords are of equal length. In a circle, if the chords are of equal length, then they are at an equal distance from the center of the circle.